Okay, so let's kind of summarize this example that we've been working with. So we've got this system of differential equations that I've written in matrix form over here. And the last set of notes, we talked about how we can find the general solution by finding the so-called eigenvalues for this matrix of coefficients. So this matrix, you can check, happens to have eigenvalues. One of them is 3, and one of them is -2. And then we found that there were two special solutions that we identified. This one was special, so if we start off with x being 3 and y being 0, that was nice because those solutions stayed on the line y equals 0. So this vector 3, 0, we're going to call an eigenvector for this eigenvalue 3. And I'm going to define this more carefully shortly. For the eigenvalue of -2, the vector -2, 1 is an eigenvector for that eigenvalue. And so this was special because we saw that if I started off at a solution where x was -2 and y was -1, that as time goes on, that point, the solution is going to stay on the line y is equal to -1/2 x. And for the solutions that were on the x-axis that started at 3, 0, for example, we noted that these solutions are going to move away from the origin as time goes on. Whereas the any initial value, any initial point that starts on the line y is equal to -1/2 x, those solutions moved in towards the equilibrium at the origin. So one observation that I want to make before we talk about more generally how we can find eigenvectors is that if the sign of an eigenvalue is positive, as in the case for the eigenvalue of 3, then the solutions on its corresponding eigenvector move away from the origin. And if an eigenvalue is negative, then its corresponding eigenvector is going to tell us that solutions that start on that vector are going to actually move in towards the equilibrium, which is the origin. So the sign of the eigenvalue is going to tell us the direction that we move on a solution that starts on one of these eigenvectors. And moreover, these eigenvalues and eigenvectors we can use to express a solution in what's called vector form. So here we had this general solution for x and y that we could write as c1 e to the 3t, c2 e to the -2t, and the solution for y was just y was -1/2 c2 e to the -2t. So we could write this in matrix form or in vector form by writing out kind of what are the terms that involve the e to the 3t over here as a product of vectors. So it's the constant c1 times this column vector of 1, 0 times e to the 3t. And then I could arrange the terms that had e to the -2t in them similarly. So I could write this as plus the constant c2 times the column vector 1 -1/2 e to the -2t. So on the next slide, I want to just kind of talk about this more generally, how we can find eigenvectors more generally, and how we can take solutions and write them in vector form, more generally speaking. Okay, so let's talk more generally about how we can express solutions in so-called vector form. And I realize we haven't talked about what an eigenvector is technically yet, so I'll do that afterwards. But given a system of linear differential equations, we can find eigenvalues, say lambda 1 and lambda 2, and then we'll talk about how we can find corresponding eigenvectors for each of them. And once I find these eigenvalues and eigenvectors, I can therefore take my general solution and write it in what's called vector form by taking an arbitrary constant, say c1, times the eigenvector 1 times e to the r1t plus arbitrary constant times eigenvector 2 times e to the r2t. Okay, so R1 and R2, sorry, are representing our eigenvalues. In particular, last time we looked at an example where we had this system of differential equations, and then we found out that it had eigenvalues of -4 and -2. And then we didn't need to know anything about eigenvectors to find the general solution. We were able to guess what the forms of x and y were, and then plug them into back into one of the differential equations to see what the relationships were between the arbitrary constants. But now, if I want to write this in so-called vector form, well, what we've got is the following. So x is this stuff over here, y is this stuff over here, and now what I can notice is for the e to the minus 4t terms, they both have a c1 in front of them. This has a 1 in front of it, and this has a 2 in front of it. So it's almost like I have the vector 1, 2 that's then being multiplied by c1 e to the minus 4t. And for the e to the minus 2t stuff, the kind of vector that we have in front of that is on the top we have 1, and on the bottom we have a minus 1/4. So if I wanted to write this in vector form, that's what I could do. I just kind of, it's almost like factoring out the constant, factoring out the e to the minus 4t, and what was left was this column vector 1, 2. And over here, I had a 1 in front of this, and a minus 1/4 in front of that. So that's where that one goes. So that's how we can take a solution and express it in vector form.